I'm going to talk about observational counterparts of systems that we think or they appear to have undergone stable mass transfer in the past. We talked yesterday quite a lot about algols, which I'm not going to talk about today. I'm mostly going to talk about the post main sequence evolution. So we've seen this diagram before. We have, say, Roche-Loeb overflow of some sort, and then we have a bunch of phases which are quite relevant in this context. First, we can focus on the donor star, the accretor star, the star that accreted mass. And we have observational counterparts which are quite promising for mass accretors in the, I forgot to mention, I'm going to talk only about massive binaries. Okay, I'm focusing on massive binaries. In the massive star regime, mass accretors, we have a very promising counterpart for this, and these are OE and BE stars. So I'll introduce them in a sec. I'm also going to talk about their strip star companions and about the more massive counterparts, which are Wolf-Rayet stars. We'll see how long, we'll see if we get there. And finally, just a few words about also this interesting phase where you have actually a black hole and star next to it. Okay. So I'm going to start with OE and BE stars, and you can already tell that I claim that this is characteristic of a certain mass range. Why is that? The OE and BE phenomenon, which I'll introduce in a second, we heard about this before, is a phenomenon that kicks in roughly at these, well, okay, M donor is maybe a bit hard to define here, but typically BE stars themselves, the accretors have masses between 5 and, actually this should be M accretor. It doesn't make too much sense, I think, to call it M donor. But it's a mass regime which is massive stars, but it's intermediate compared to the more massive stuff that I'm going to talk about later. OE and BE stars are a spectral type. They're O stars or B stars, so typically masses between 5 and 20 solar masses, and they have these strong emission lines in their spectra in the Balmer series, which are characteristic of disk profiles. Okay, so we know that these are stars with disks. Typically, they rotate very rapidly, so the physical image of these stars is quite clear. These are rapidly rotating stars with disk. It was suggested already for a while now, a few decades ago, that these stars could be prominent mass accretors in binaries. Why should stars start rotating very rapidly and develop decretion disks? And the idea was, of course, a binary interaction. There has been a debate, which is to a certain extent still ongoing. Are all BE stars binary products? Are some of them binary products? In the last years, we've been hearing more and more of evidence that shows that the vast majority of BE stars are binary interaction products. I want to highlight Julia's work here, in which we looked at massive BE stars. And if you think about it, if a BE star is a mass accretor in a binary, you would expect the companions of these stars to be funny, evolved stars, maybe neutron stars or helium stars, or maybe they're runaways of some sort. You would not expect to find normal, boring main sequence stars in close orbits to BE stars if these are accretors. And this is indeed what you observe. So there's hardly any, or maybe potentially none, example for a massive BE star with a main sequence companion. There is also indications that many of these BE stars are close binaries. You can see that their disks are being truncated by some companions nearby. And many of these BE stars also have detected helium star companions, so stars that lost their outer layers. And we'll talk a little about this. So why are these systems so exciting? Because if you can measure the mass ratio and the periods of these systems, they give you very sharp constraints on mass transfer, which is what this workshop is about, mass transfer stability and all of that. So how do we go about getting the masses of these two companions? These are not very easy systems. First of all, as I said, many of these BE stars are thought to have helium star companions, the donor that got stripped and lost their outer layers. And you may ask yourself how bright these stars are typically. So I guess most of you know these are hot objects. They're very compact. They emit most of their light in the UV. So this is an image taken from, from Ylva Gutberg's paper, where you see a spectral energy distribution for stripped star, and compared to a few normal, say, main sequence stars of different spectral types, or if you're more comfortable, simply different masses on the main sequence. And the takeaway message is that if you look at the far UV, which is where measuring the strip star is most favorable, say with instruments like HST or FUSE, it will be hard to see the strip star if you have a companion that is, say, B1 or earlier. Yeah, so these are not objects that are easy to detect. So what detections method do we have for the strip stars? One of these methods, I think we heard of already, and we might hear later, is photometric UV excess. So if we go back to this image, you see that, for example, if I look at the B8 star, a stripped star would cause a huge, tremendous UV excess, and suddenly you'll see, you know, a standard boring B star, but it has like a very bright UV counterpart. So this tells you, okay, there's something hot going on there. So you can try and look for stars that have this UV excess, and this is a powerful method. And we recently, I mean, from Ylva Göthberg and Maria Draut, we just heard of the first such sample. It was discovered like this. It is relatively cheap because it uses photometry, it is systematic, but the downside is that you need the strip star to contribute substantially to the UV light. So one of the things that it means is that if you look for strip stars like this, you're probably going to be relatively biased against stable mass transfer system, because stable mass transfer system will have accretors which are typically much more massive and early type compared to the hot stars. Okay, so that's important to keep in mind. There's also the possibility to look at UV spectra and use techniques such as cross-correlation to try and hunt for very faint features of the strip star in the UV. This goes to a few percent. Typically, you can detect things that are at the level of a few percent UV contribution, but it needs high signal-to-noise UV spectroscopy, which is quite expensive. There's another phenomenon which is quite interesting. Many of these strip stars show something that we call trailing emission in the optical spectra. You see that the strip star is moving, and there is this trailing emission, optical emission lines. It's not clear what the origin of these lines are, but what is clear is that they're tracing the orbit of the strip star. We have quite a few evidence for this. And these are strong features. So sometimes they're also used to determine how the strip stars are moving. And finally, we also have interferometry, where you can really resolve the two objects in the sky. And this is a powerful method, but again, it only applies to systems that are relatively nearby. Okay, so all these methods were used, basically. This is not a complete sample of strip stars that we have in the galaxy, but it's a substantial sample of them. So this is taken from Lucian Wang's paper in 2021. And you can see a collection of such strip stars that were measured, different techniques. Here I'm also showing the population of strip stars measured in the Small and Large Magellanic Cloud by Maria Draut and Ylva Göthberg. Again, they were found with different techniques, so they probe different regimes. I'm not going to talk about this sample, partly because we don't have the orbits for the sample yet, so we don't know what the mass ratios of these objects are. I'm going to focus mainly on the galactic counterparts. So we'll get to some results and some conclusions soon. Before we do, there's another type of strip stars that have emerged in the last years, which are quite exciting. So you saw this video probably before, and also I showed it before. You know that the donor star is now going to contract on a thermal timescale until it starts burning helium in its core. But the contraction phase takes some time, so yeah, thermal timescale, and you can catch the strip star as it is contracting. It is, of course, pretty rare to catch them at this phase, but on the other hand, they're still very bright at this phase. So we also started finding a new class of strip stars, which are these bloated strip stars, which we're now finding more or less everywhere. So funnily enough, the place where we started finding them are systems which were thought originally to host black holes. We now call them black hole imposters. Something about the strip star, the fact that they're overluminous and they're bloated, gives them the appearance of more massive stars. They led to a lot of confusion and caused people to believe that they have black hole companions. And it turned out that all these systems actually are these rare, unique, evolved binaries with loaded strip stars. So you can also use these systems to get constraints on the mass ratio and the period and all of that. The challenge here is that the OE and BE stars are very rapidly rotating. They're hardly moving. They're very heavy, right? And the strip star is the easiest. The bloated strip star is easy to detect. So you see an example for the spectroscopists among you, how this actually looks like. You see an absorption line that traces the bloated strip star, and you see it overlaid on some kind of an emission feature, which is coming from the disk of the BE star. Not super easy to solve, but it's doable. One of the techniques we've been using quite a lot is spectral disentangling. For this, I'm not going to talk too much about this, but this is a method to determine the mass ratios of such systems. Okay, I'm going to jump to a diagram that I prepared, compiling all the stripped star plus OEBE systems that exist in the literature in the galaxy, including the bloated ones. So the bloated are marked as triangles, and the hot strip stars are marked as small symbols. The color denotes the estimated mass of the strip star. What I want you to note are what I'm plotting here are the periods of the systems and the mass ratios. So what is the take-home message? That first of all, the mass ratios of the systems are extreme. Some of them go as extreme as 0.1 or so. And the periods are quite long. What does it, and one thing that I want to mention is that all of these systems are circular. We had quite a lot of talk about whether or not post-interaction systems are circular, whether there's eccentricity pumping, all of that. All of these systems are circular. What does it tell us? First, it tells us that to get such extreme mass ratios, the mass transfer had to be very close to conservative. Okay, so you had almost all the mass that was stripped from the donor was transferred to the second object. It also tells us that somehow, even though stars, the accretor starts spinning very rapidly, and we see that, it can continue accreting mass. So yesterday in Pablo's talk, we heard about how stars might lose winds and might not accrete anymore, but these stars manage to continue accreting even though they spin at close to critical rotation. Why, how, not clear, but this is an observational fact. And the fact that they're circular is also interesting. So it seems that at least for these systems, the mass transfer really either circularizes or at least does not pump the eccentricity. So how can stars continue accreting while rotating? Well, we heard about this quite a lot. I wanted to talk about one quite exciting system that has been known for a while now, but we're trying to converge on an actual final solution for the system. It's called Plaskett star. It's a binary with a known magnetic star. It's the donor star is a stripped, bloated kind of star. It weighs about 2 to 3 solar masses. The accretor is about 30 solar masses. The period is about 10 days. And the special thing about the system is that the accretor is magnetic. It's a very, very weird system. It's a rapidly rotating supermagnetic star. The donor is very close to filling its Roche lobe. And the question is, first of all, it's very tempting to think that the magnetism is related to the fact that the star just accreted mass, and there is some kind of tidal maybe interaction there. And it's tempting to think that these magnetic fields might have something to do with the stars being able to continue accreting. So that's why I think it's important to remember these magnetic systems. Let's see how I am with time. A few more minutes. So this was about the intermediate mass, massive systems. I'm going to now jump into a more massive regime where things maybe are exciting on the one hand, but more difficult on the other hand. And the best probes here are actually Wolf-Rayet stars. So Wolf-Rayet stars are the massive counterpart of the stripped stars we've just talked about. These are stripped stars that in our galaxy would have initial masses of at least 20 solar masses, current masses of at least 8 solar masses or so. Okay, what do we know about these Wolf-Rayet stars? First of all, what are they? So we had quite a few questions also yesterday. How do you know if it's a Wolf-Rayet star or a stripped star and so on? For an observer, it's very easy. Wolf-Rayet star shows strong, broad emission lines. It's a hot star that shows strong, broad emission lines, and these emission lines are characteristic of stellar outflows. So it's a star that for some reason loses a lot of material. And the reason is clear by now. We know that these are stars that are relatively close to the Eddington limit. Their luminosity to mass ratios are very extreme. So classical Wolf-Rayet stars are post-main sequence stars. They kind of maintain the same luminosity they had on the main sequence, but they lost a lot of their outer layers, and now they're much closer to the Eddington limit. And these are per definition stars with strong winds. I'm going to skip this one, because it's not actually relevant. Now, one question that you want to ask is, do we know that these objects are binary interaction products? If we want to use them to probe how mass transfer happens for these very massive stars, do we know that they're binary interaction products? And actually, this is not a trivial question. So one thing that is clear is that it's a metallicity dependent question. So here you see examples for 2 evolution tracks for a 40 solar mass star. In the galaxy, you see that the star is kind of like, it's a single star model. So it's kind of like evolving its life, losing mass at different phases. It doesn't have to be the correct truth, yeah? But according to this model, it eventually goes all the way to the hot part. It manages to strip its outer layers and become a Wolf-Rayet star. On the other hand, on the right panel, you see that the star is not really capable of getting rid of its outer layers. This has become, because at low metallicity, we know that winds are weaker. So you might think that at low metallicity, most of these Wolf-Rayet stars must be binary interaction products, because how else can they get rid of their outer layers? And that's something that is also unfortunately not as trivial. And this is also, I think to you might be interesting. So as you go to lower and lower metallicity, what you observe is that Wolf-Rayet stars, these are the populations of Wolf-Rayet stars in the Milky Way, large and small Magellanic Cloud. And as you go to lower metallicity, you observe that Wolf-Rayet stars, this phenomenon of emission lines and winds kicks in at higher luminosities. You would only see Wolf-Rayet-like spectra at higher luminosities. So at the SMC, for example, Wolf-Rayet stars come from stars that are initially 35 solar masses or so. So we don't, the problem is that at the SMC, it's true that stars find it harder to strip themselves, but stars also find it harder to appear as Wolf-Rayet stars. In other words, the bottom line is that it's not easy to know which Wolf-Rayet stars are binary interaction products and which Wolf-Rayet stars are the potential result of single star evolution. This is still an open question. I wanted to highlight a few, I have just a few minutes, so I'm not gonna spend too much time about this. I wanted to highlight a few studies that we're now leading to hunt for potentially unseen companions to these Wolf-Rayet stars in the Milky Way and the large and small Magellanic Cloud. But actually the results are more or less conclusive across the field. We're not missing too many companions. So it seems like about 50% of the Wolf-Rayet stars are truly single. What that means is not clear. Whether they really evolved as single stars, whether they're mergers or something like that. I just want to show an equivalent diagram that I showed you before. This is a bit outdated, but it didn't change too much. You have the period versus the mass ratio. And the problem is with these systems, it's much harder to interpret these diagrams because of the mass loss of Wolf-Rayet stars. This is another ingredient which introduces uncertainty. But people who have tried to look at specific Wolf-Rayet binaries, like this study by Petrovich et al., they concluded that at this mass regime, we find indications that the mass transfer is strongly non-conservative. Okay, so for some reason at the upper mass end, the mass transfer appears to be less conservative than it is in this intermediate mass range that I highlighted before. I also wanted to show this diagram, which I find quite interesting. We talked about eccentricity and eccentricity pumping. So here you have a diagram of periods versus eccentricities of various well-established orbits of Wolf-Rayet binaries in the galaxy. And you see that below, say, 25 days or so, this is a logarithmic scale, all the systems are close to circular. You cannot trust the errors, let's say, are the order of 0.1. But above that threshold, you do start seeing eccentric binaries, substantially eccentric. This could mean two things. Either these eccentric binaries never interacted in the first place, which is a big question. Yeah, it's possible that, say, a binary at a 100-day period, that the Wolf-Rayet progenitor never actually expanded to large enough radii to interact. Or there is some kind of an eccentricity pumping mechanism happening here, which for some reason doesn't happen at the intermediate mass regime. It's an interesting thing that we don't really understand. I'm not going to talk about black holes. I'm sorry. That's too much. I'm just going to leave it in a summary. So, as I said, in the intermediate mass regime, we have observational evidence that the mass transfer can be, I'm not saying in all cases, but the mass transfer can be highly conservative in spite of rotating the star at close to critical, and that these post-mass transfer systems are all circular. At the upper mass regime, there are indications for non-conservative mass transfer. Accretors, that's something I didn't talk about, but the companions of Wolf-Rayet stars appear to rotate substantially lower than critical, maybe 100, 200 kilometers per second. So somehow they spin down. It's not really something that models predict. And many of these post-mass transfer systems in the upper mass regime are not actually circular, if they are post-mass transfer. So this was my attempt after yesterday's night to summarize. So I hope you could follow that, and I'm done.
Your original bike runner is sick.
So I would like to go back to when you say that most of the Wolf-Rayet stars are apparently already known and observed. I'm not sure I'm following how the people that you're citing have estimated this in particular. I mean, did they do like a population study, or
Do you mean observationally that I claim that most of them are known?
Yeah.
I don't know if I said it in this talk, but it's true. The reason that we think that the Wolf-Rayet populations are relatively complete is because they are relatively easy to detect because of their emission lines. It has nothing to do with population study. You don't mix theory there.
But so, I mean, you can see Wolf-Rayet stars even if you have like dust or gas in front of you.
No, so you could have some problems with dust and extinction and maybe very bright companions which are overshadowing the Wolf-Rayet star. There could be still some biases there. But we, the community, don't think that it's a significant fraction of Wolf-Rayet stars that we're missing.
The Milky Way, we miss
That's true.
a lot, right?
Yeah.
I mean, we missed the half of the Milky Way, which is on the other side of the galactic center, because they are in the plane. I'm sorry.
Okay. Of course, yeah.
Yeah, sorry for the people online. I was mentioning that in the Milky Way, we probably miss a significant fraction of Wolf-Rayet stars. Us, we miss a significant fraction of stars simply because of the extinction in the galactic plane. And most of the Wolf-Rayet stars, because they come from massive stars, they are to be found in the galactic plane. In the LMC and the SMC, I think we are, I would 100% concur with you. And in the halfway or the part of the galaxy for which we can observe, I also agree with Tomer.
Sylvia, you had a question online?
Yeah, thank you, Tom. It was really nice talk. Very intriguing results. I was wondering if you can comment on which mechanisms we have for the stars to keep accreting, even though they're close to critical. So do we say fields or, and if somebody else in the room wants to comment, that's fine too.
I'm happy for somebody else in the room to comment.
I don't really want to comment on the question. I want to add another question to this. Like I know we've heard that all the models basically say that a tiny fraction of mass is enough to spin up to critical, but another solution of this could be that it is actually not that easy to get to critical in the first place. And I was wondering if someone wanted to comment on that.
Maybe I can add something. Well, I mean, first of all, there is like how you define critical rotation that is already a problem. I mean, if you, I mean, most of us here are like MESA users in general, but if you instead like Geneva GENEC users, they prescribe critical rotation in a completely different way. So technically, when you say, for instance, when you prescribe a rotation of 20% critical velocity, it means a different kilometer per second if you are using MESA or if you're using GENEC. So there is still this variability.
I would add to this in saying that we usually neglect the angular momentum transport between the accreting star and the accretion disk that's forming. There are some instances in which people theoretically expect that the disk, just the fact that there is a disk, there should be some angular momentum transport, and that might ease decrease sort of the amount of angular momentum that's accreted on the accretor, and then it just can accrete more before actually reaching critical.
Yeah, also from a theoretical perspective, I think it's hard to imagine that it's hard to spin up a star, because a star has all its mass in the center with zero moment of inertia because it's on the rotation axis. And then you have a fluffy envelope that you just blow on it and it's gonna start spinning easily. So I think from there, like theoretical reasons why that are pretty solid of why we think it's easy to spin up a star. But then, yeah, angular momentum transports, which we don't understand at all, instead could change these, but I have a hard time imagining how this makes it very hard to spin up a star.
I guess one can also think of a practical question. I don't know what most of you do when you do population synthesis and your stars get to critical very quickly. What do? Do you stop accretion? No.
There's no critical rotation in populations. Yeah,
okay.
you don't have
no
it.
such
You
a thing.
just place an
Yes.
envelope onto a other star, and then you say what fraction does make it to the other star?
Right.
You just vary that between 0 and all.
In detailed evolution, that could be an issue. In detailed.
Yeah, if you do large runs of Mesa, then I think it by default says there's nothing accreted, which is related to that critical rotation rate. So there's this. That's what Kuchik showed yesterday. I think Sylvia also. Sylvia, you can unmute.
Yeah, no, regarding what you said, but in print, I agree with you that in principle, either in detailed and in fast codes, there's just a parameter, which is the accretion efficiency, and that's what the code then will continue with. But that value can just be a constant value, but you can also come up with some other prescription for it, right? So many PopSyn codes have this criterion that's based on the thermal time scale versus the mass transfer time scale. But the way that you answered it kind of made me feel like in a fast code it wouldn't be possible to come up with a criterion that's based on the stellar rotation. But I think there's no difference there between a fast code and a.
No, you're right. Yeah, I'm sorry. I indeed meant there is indeed the default also in Compass is that it's based on the thermal time scale, but that still gives you a very specific pattern of the accretion efficiency as a function of mass, essentially, and you can change that to whatever you want. But there's no actual following what I meant is there's no actual following of the rotation of the accreting star. So it's something that you would fit to what it would be.
But it would be possible, right? Like some PopSyn codes, they do rotation of the stars. And of course, you have to then assume solid body rotation.
Yeah. Yeah.
A priori impossible. We've just not done it.
Well,
we have we're about to move on.
Okay, well, I can just I think this answers Sylvia's last point that in PopSynth you would need to assume rigid body rotation because you don't have the internal structure. That might not be that terrible because even assuming a Spree-Taylor dynamo, which some people like Jim Fuller say it's too weak, in my detailed models, I reach rigid rotation pretty fast during the mass transfer phase. So that might not be terrible compared to many other things in rapid PopSynth, right? So